Off the California coast, beneath 40 feet of cold Pacific water, a forest grows. It spans continuous miles of canopy, moving in slow current below the surface. It is harvested on a fixed industrial schedule. Aquatic combines move through this underwater canopy at low vessel speed, mowing the upper fronds and pulling wet biomass onto a barge deck. This is not a fishing operation. The cargo is bound for a chemical extraction plant. See, California's giant kelp beds span an estimated 150,000 acres of Pacific coastline, and a controlled fraction of that biomass processed each year produces sodium alginate, a stabilizer found in ice cream, pharmaceuticals, textiles, and dozens of processed food categories worldwide. If you follow industrial food supply systems at this scale, subscribe to this channel and leave a like. Have you ever noticed sodium alginate on a food label before today? Drop that in the comments. The extraction sequence is already underway. The target species is Macrocystis porifera, giant kelp, the largest seaweed organism on Earth. Individual plants reach over 150 feet in length, anchored to the seafloor by holdfasts and growing vertically toward the light. California's central and southern coast supports one of the most extensive natural stands of this species on the Pacific. Under optimal water temperature and nutrient conditions, giant kelp grows at up to 2 feet per day, one of the fastest growth rates of any plant organism on Earth. This rate makes it a viable, renewable biomass source. Harvest rotations are designed so that regrowth replenishes the cut zone before the next scheduled run. California's Department of Fish and Wildlife zones the active kelp beds by county and issues annual harvest permits with tonnage limits per zone. Operators file post-harvest yield reports that feed into the following year's quota allocation. GPS-integrated navigation keeps vessels within permitted boundaries during each harvest run. Harvest timing is set by canopy density surveys, water temperature data, and permit cycle windows. A dense, healthy canopy supports a cut. A thermally stressed or undersized bed is bypassed until survey data confirms recovery. No crew goes out to a zone that cannot sustain the run. The harvest vessel is a modified barge platform, typically 80 to 100 feet in length. A cutting assembly is mounted to the bow designed to mow the kelp canopy 3 to 4 feet below the waterline. The platform advances at low throttle, slow enough for the collection system to keep pace with the cut volume. The cutting heads use reciprocating steel blades, mechanically similar to agricultural mowing equipment adapted for marine use. Severed fronds are guided by water flow and onboard conveyors into a collection hopper on the vessel deck. The cutting cycle runs continuously at operational speed. A single harvest run accumulates between 100 and 300 wet tons of kelp biomass on the barge deck. The material arrives dense, salt-soaked, and tangled in its own frond structure. Deck crews monitor load distribution and vessel trim as the collection builds toward capacity. When the permitted quota for the run is reached, the vessel turns back toward the receiving dock. Transit time from offshore beds to coastal processing facilities ranges from 2 to 6 hours, depending on the bed location relative to the port. No refrigeration is required during transit. The biomass is stable at ambient marine temperature. At the receiving dock, a crane or conveyor system offloads the wet kelp onto a weigh station platform. Each load is logged by wet tonnage, tagged with the harvest zone identifier, and entered into the state yield tracking system. Processing begins within hours of dock arrival. From the weigh station, the kelp enters a pre-wash line. High-pressure jets strip sand, sediment, and surface debris from the incoming biomass. The wash stage also begins regulating the salt load in the material before it enters the chemical treatment sequence. After washing, the material moves into a shredding system. Industrial rotary cutters reduce the long frond material into 3 to 6 inch fragments. This size reduction increases surface area and allows the subsequent chemical treatment to penetrate the cell wall structure uniformly across the batch. The chopped kelp enters the first chemical treatment stage, an alkali pre-soak bath using diluted sodium carbonate solution held at 60 to 80 degrees Celsius. This breaks down the cellulose and protein matrix within the kelp cell walls, releasing the alginic acid salts bound within the tissue. From the pre-soak, the material moves into high-temperature extraction tanks. Steam-heated vessels hold the treated biomass at 80 to 100 degrees Celsius. At this temperature, sodium alginate dissolves from the cell structure into the surrounding liquid phase, forming a viscous extraction slurry. The result is a thick, viscous slurry, sodium alginate suspended in liquid alongside insoluble fiber, pigments, and residual minerals. The first filtration stage separates this alginate liquor from the raw fiber fraction. Industrial rotary drum filters or belt press units handle the separation at continuous flow rates. The fiber residue removed at this stage is the first major byproduct stream of the operation. It carries significant organic material, residual protein, minerals, and structural polysaccharides from the kelp cell wall. This fraction is collected and directed to a secondary processing line. To control color and reduce pigment carry-through, the filtered alginate liquor passes through a bleaching stage. Sodium hypochlorite solution is metered into the flow at controlled concentrations. This shifts the extract from its natural brown-green tone toward the pale cream color required for food and pharmaceutical grade specifications. Following bleaching, the liquor enters the precipitation stage. A diluted acid, biomass hydrochloric or sulfuric, is added to the flow, dropping the pH below 4. At this point, the dissolved sodium alginate converts to alginic acid, which is insoluble and precipitates out of solution as a gel-like mass. The precipitated alginic acid mass is separated from the acid liquor in decanter centrifuges. Industrial centrifuge units run continuously, spinning the gel mass outward against the bowl wall and expressing the waste liquid through the liquid outlet. The retained solid is alginic acid at approximately 80% moisture content. The separated alginic acid gel is reacted with a sodium hydroxide solution, neutralizing the acid and converting the material back to sodium alginate. This conversion step is where food-grade and pharmaceutical-grade product identity is formally established. pH is monitored continuously throughout the neutralization reaction. The sodium alginate slurry enters a secondary filtration sequence, multiple passes through progressively finer filter media. This stage removes trace fiber fragments, residual pigments, and mineral impurities that pass through earlier separation steps. Purity levels approach final product specification at this point in the process. The filtered slurry moves into a drum drying system. Large, heated, rotating cylinders spread a thin film of the slurry across the drum surface. The material dries rapidly as the drum turns, and dried flakes are continuously scraped from the drum face by a doctor blade assembly mounted at the discharge point. The dried flakes enter the milling line. Pin mills or hammer mills grind the material to a specified particle size range. Particle size controls the dissolution rate and the viscosity profile of the finished alginate powder. Each application grade requires a different milling target. After milling, each production batch is sampled for viscosity testing. A defined concentration of the powder is dissolved in water and run through a viscometer. The reading, measured in centipoise, determines which application grade the batch qualifies for. Food, pharmaceutical, textile, or industrial. Batches meeting food-grade thresholds are tagged and moved to hygienic packaging lines. Pharmaceutical-grade batches require an additional documentation set, full chain of custody records, certificates of analysis, and processing verification logs for each production step. The paper trail for pharmaceutical product follows every kilogram. Packaging for industrial and food-grade distribution runs in 25-kilogram multi-wall paper sacks. Filling stations operate under low humidity conditions to prevent caking in the hygroscopic powder. Labels carry lot number, moisture content, viscosity grade, and country of origin, required for customs compliance at destination ports. Filled sacks are palletized and moved into humidity-controlled warehouse staging areas. Sodium alginate absorbs ambient moisture and will cake if storage conditions are not maintained. Pallet stacks are stretch-wrapped and staged for container loading within defined shelf life windows. Container loading connects the processing facility to the global distribution network. 40-foot dry containers lined with desiccant panels to control interior humidity receive pallet stacks of finished alginate. Shipping manifests, certificates of analysis, and export documentation are prepared in parallel with the loading operation. From the loading dock, containers route through California's major Pacific ports toward receiving markets across the United States, Europe, and East Asia. Dairy processors represent one of the primary downstream application segments. Alginate enters these formulations as a functional ingredient, stabilizing, thickening, and binding. In ice cream manufacturing, sodium alginate controls ice crystal formation during freezing and cold chain cycles. A concentration of 0.1 to 0.5% by weight prevents the texture degradation that occurs when finished product experiences temperature variance in transit and retail storage. The function is invisible to the consumer but measurable in every bite. Cream cheese, processed cheese, and yogurt formulations use sodium alginate to maintain gel structure and prevent syneresis, the separation of liquid from the product body over shelf life. The polymer holds the aqueous phase inside the product matrix from packaging through retail display. The pharmaceutical sector represents a separate and high-value application stream for California alginate. Sodium alginate's ability to form a gel in contact with calcium ions makes it the primary material for wound dressing products. Alginate dressings absorb wound exudate, maintain a moist healing environment, and are removed from tissue without mechanical damage. In tablet manufacturing, alginate functions as both a binder and a controlled-release coating material. A tablet coated with an alginate film can be formulated to dissolve at a specific digestive pH, enabling targeted delivery of the active ingredient. This is a functional pharmaceutical role with direct dosing implications. Textile printing operations consume significant volumes of sodium alginate as a print paste thickener. When mixed with reactive dyes, the alginate paste controls viscosity precisely enough to allow fine-line dye application without bleed. Industrial fabric printing operations globally depend on consistent alginate viscosity grades for repeatable pattern quality. Brewing facilities use alginate-based clarifying agents in fermentation and conditioning vessels. The alginate flocculates suspended proteins and yeast cells, pulling them out of solution and improving final beer clarity. This application uses industrial-grade alginate produced to brewing-specific specifications and is standard across commercial brewing operations. Paper coating operations apply sodium alginate as a surface sizing agent in commercial paper manufacturing. Alginate-coated paper carries improved ink holdout and reduced surface roughness, critical properties for printing paper grades. This industrial application consumes large volumes of lower-purity alginate produced at scale. Wet pet food formulations use sodium alginate to build gel texture in canned and pouch products. The alginate concentration in the formulation determines the viscosity and texture of the finished product. Given the global scale of the pet food manufacturing sector, this represents a high and consistent volume application for alginate supply. Toothpaste manufacturing uses sodium alginate as a binder and rheology modifier in the paste matrix. The alginate controls the flow behavior of the product, consistency in tube dispensing, and on-brush texture. Purity specification for this application aligns with food-grade requirements and carries FDA GRAS designation. In the United States, sodium alginate derived from seaweed is classified as generally recognized as safe by the FDA. This GRAS designation permits its use in food formulations without product-by-product approval review, provided the ingredient meets purity specifications and is applied within accepted concentration ranges for each food category. Every production batch processed through a registered food or pharmaceutical facility carries a complete documentation chain: raw material source, harvest zone, processing dates, reagent lot numbers, test results, and final packaging records. This record set is the compliance basis for FDA-registered operations and for import certification requirements in receiving markets internationally. Processing water generated through the extraction sequence is managed under industrial effluent permits. Wash water, spent acid liquor, and alkali solutions are either treated on-site in wastewater treatment systems or contracted to licensed industrial waste facilities. Closed-loop recovery reduces discharge volume where the process chemistry allows. The fiber residue from first-stage filtration is collected and reprocessed as a byproduct stream. At select facilities, this material is treated or composted to produce a seaweed-based biofertilizer carrying trace minerals, organic nitrogen, and residual polysaccharides. The byproduct offsets raw material waste within the overall mass balance of the operation. California's kelp harvest quota system is updated annually based on aerial survey data and underwater transect measurements. Some permit renewals require operators to submit prior year yield compliance reports. The system is structured to prevent successive overharvest in any single bed zone across multiple seasons. Environmental monitoring teams conduct scheduled transect surveys in active harvest zones. Measurements cover canopy density per unit area, holdfast count, and species composition across survey stations. The data feeds directly into the quota modeling calculations used by state permit administrators each season. Annual kelp harvest volume from California's permitted zones has historically ranged from 100,000 to 170,000 wet tons per year, varying with ocean conditions and seasonal demand cycles. From this harvest volume, dry sodium alginate yield typically runs between 15 and 25% of the processed dry weight input. California processed sodium alginate enters a global market shared with producers in Norway, Chile, China, and Ireland. The California supply is distinguished by proximity to Pacific macrocystis biomass, established regulatory infrastructure for food and pharmaceutical grade verification, and documented supply chain traceability from harvest zone to finished product. At the processing facility, extraction tanks run in continuous batch sequences timed to harvest vessel arrivals and warehouse staging capacity. Workers on the extraction floor manage chemical dosing, temperature holds, and centrifuge throughput across overlapping batch cycles. The system does not pause between vessel runs. The cycle dictates the schedule. The last container is sealed. Before dawn, trucks depart the facility yard carrying finished product tagged for dairy manufacturers, pharmaceutical distributors, and food ingredient brokers across 3 continents. On the Pacific coast, the kelp canopy has already begun to regenerate. The next harvest cycle is already scheduled. The system does not stop. Under this video, there's a subscribe button. So it's a small action, but it helps document how water becomes food at scale. If you found this system worth following, leave a like. And tell us, where are you watching from? Have you ever worked in aquaculture or seafood processing?